Hi, it's Friday, July 3rd, 2020. My name is Noah Seeley, and welcome to my channel. So today we're going to be finishing our discussion on the asynchronous methods for deep reinforcement learning paper by the Google DeepMind's team. This is the second part of this video series for this paper, so if you've missed the first part, I'll link it in the description below. In that video, we talked about the introduction, related work, and reinforcement learning background sections of the paper. Today we're going to be discussing the asynchronous RL frameworks, experiments, and conclusions and discussion sections of the paper. Before we get into it though, if anything related to reinforcement learning still feels a little bit fuzzy to you, I'll link my two-part introduction series to reinforcement learning in the description below. They're quick videos that briefly introduce the definitions, processes, and applications of reinforcement learning. If you feel like you're all caught up though, without any further delay, let's finish off this paper. So the asynchronous RL framework section starts by discussing that the team's goal in this section is to create an asynchronous multi-threaded variant of various algorithms, such as the one-step queue learning, SARSA, n-step queue learning, and actor-critic advantage. Most of these algorithms were lightly discussed in the part 1 video to this series. They mentioned that while all the listed algorithms are quite different, they have two main ideas that will standardize all of these algorithms in order to make them practical for their goal. So for starters, they will use actor learners as seen in the Gorilla framework from the first video, but here they will execute everything separately on different cores of a CPU. They note that keeping the learners on the same machine takes out a lot of the communications cost of using multiple machines, allowing them to use a more expensive type of parameter update. The second idea is that running multiple actor learners in parallel will be likely to expose each actor to different parts of the same environment, and that they can actually use different explorative policies for each agent to maximize this result. The use of varying policies makes the online updates between agents running in parallel less likely to be correlated. As we saw in the last video, this was the issue that Experience Replay corrected, and is necessary here as this asynchronous framework is trying to replace Experience Replay to fix the problems that Experience Replay itself causes. Thus, Experience Replay is not used in these actor learner agents. This elimination of Experience Replay will also make training more efficient, as well as allow the use of on-policy algorithms such as SARSA. So the next subsection is basically describe how the team implemented the framework using each of the listed algorithms. I'm not going to delve very deep into each of them, but some notable points are that 1. With Q learning, the team found that giving each agent its own explorative policy improved overall robustness of the agent. They note that it improves performance in terms of exploration. 2. SARSA is basically a ditto for what they mention in Q learning. 3. The n-step Q learning subsection discusses how more calculations are made in each gradient update compared to single-step Q learning, as n-step Q learning will calculate a value for rewards up to the max time step. These calculations are done in a single update step. And 4th, the team uses a CNN as well as entropy regularization for actor-critic advantage algorithms. I think the important takeaway from this section is that these are the algorithms which the team decided to conduct their new research upon. This section ends with a note on optimization. It essentially says that they implemented an alternative update, which research has shown to be more robust than previous implementations. So onto the experiment section. This is actually a pretty long section, but to summarize, the team tested their new implementations of reinforcement learning algorithms on various testing environments. These environments included the Atari games benchmark, which we now all know and love, the TORCS 3D car racing simulator, as well as the A3C Mujoco and Labyrinth, which are a physics testing and maze simulator, respectively. The next 4 subsections go into detail of each of the listed testing environments. To summarize, 1. On the Atari benchmark, it was found that the asynchronous implementations could outperform the original DQN agent the team was comparing, all while using a CPU instead of a GPU. They also found that the n-step algorithms were more efficient than the corresponding single-step ones. 2. Results from the car racing simulator showed that the actor-critic advantage algorithm would perform superior compared to all the other asynchronous implementations tested. 3. The asynchronous actor-critic advantage implementation also performed well on the Mujoco physics simulator challenges during testing. And 4th, the asynchronous actor-critic advantage implementation was able to find a reasonable strategy for the labyrinth puzzle maze simulator, which was noted to be substantially more difficult compared to the previous previous testing environments. The scalability and data efficiency subsection summarized to say that the team's hypothesis was correct, and that as agents are executed in parallel, they learn more efficiently as they are able to learn as many agents in many different states, all at the same time. The robustness and stability subsection includes the team summarizing results, saying that the agents they created are both robust and stable, as they performed well according to their results in the deployed testing environments. So lastly, the conclusions and discussion section just sum up the whole paper. The team was able to implement asynchronous versions of various algorithms, single-step queue learning, SARSA, n-step queue learning, and an actor-critic advantage algorithm. This was in order to substitute experience replay, as it proved to be inefficient for a number of reasons, such as its time and space inefficiency and its inability to implement on-policy RL algorithms. They trained these asynchronous implementations using a multi-core CPU rather than a GPU, and were still able to outperform previous reinforcement learning agents, such as the original DeepMind DQN. The actor-critic advantage implementation performed especially well, but all proved to be robust and stable. Although they aim to replace experience replay, the team also comments how implementing experience replay to the possible asynchronous implementations may actually be useful. So the paper ends by suggesting some other various improvements to both the algorithm and its architecture that could be implemented, which were taken from other reinforcement learning advancements that were recent to the paper, that for time's sake I'm going to leave out here. So yeah, that concludes our discussion on the asynchronous methods for deep reinforcement learning paper by the Google DeepMind team. I hope you were able to learn a lot from this paper, as it's a great example of the topics related to reinforcement learning that don't have as much of a direct correlation to the DQN agent that we've been reviewing thus far. There were also some more technical bits in today's sections that I did not delve as much into, so as always, I've linked all resources that I've used in the description below for you guys to go check out yourselves. If you feel that I missed anything or got anything wrong, please let me know in the comment section below. That's all for today. Thanks for watching. See you tomorrow.